So we start our video lecture 4, and so we are back to this diagram again. Now, continuing with what we're talking about. Now, we are talking about this diagram that you always see. And you're asked to find out the degree of freedom. And the point is, when we have to find out the degree of variance, we know, remember the triple point, we're talking of the triple point. Okay, so we have, if at the triple point, then you have all the three middle phases coexisting in equilibrium. So we have P is equal to 3. At the moment we come to this value of C, we have a problem. What is the composition of sillimanite, kyanite and andesite? Let's say all the minerals, sillimanite, kyanite and andesite, have the formula Al2SiO5. Let's say it has the formula Al2SiO5. So then you could write you could have AlSiO, 3 components, or you could have Al2O3SiO2, 2 components, or you could have Al2SiO5, 1 component. We take 1 component because it's the minimum number of components, right? So our C is equal to 1. And then we come to this F is equal to C minus P plus 2, and this holds up to 1 minus 3 plus 2, and this is equal to 0. Now, interesting, the degree of variance is equal to 3, or the number of variables minus the number of equations is equal to 0. That means the number of variables and the number of equations that you have is 0. Now you can ask me, so what are these equations you are talking about? What are these equations you are talking about? Where are the equations? I don't see the equations. Where are the equations? Now this is where I will explain it to you a little later. Please imagine that there are equations. And I will have to talk about it because it's not a very simple thing again. But imagine there are equations. So the number of variables here is 0 for this. The number of variables is equal to, therefore, the number of equations. And as I said, you can ask me, so where are the equations? We will talk about it a bit later. For the moment, you know from those first two chapters that, just briefly, that G is a function of pressure, temperature and composition. Isn't it? Pressure, temperature and composition. Whatever the equation is, it's a function of pressure, temperature and composition. For a pure phase, X is no more there, because for a pure phase the mole fraction is 1, so X is equal to 1. That means an equation comes in, X is equal to 1. Right. So then G is a function of temperature. So essentially when you write a reaction, say for example, kyanite is equal to sillimanite, since sillimanite has a free energy equation and kyanite has another free energy equation, and you write it kyanite is equal to sillimanite, then you will have a reaction where at equilibrium free energy of kyanite is equal to the free energy of sillimanite. So delta G, free energy change of the reaction, is equal to 0. So then you have an equation which is essentially a function of pressure and temperature. Have you understood? There is a pressure and temperature. These are the two functions. I will repeat again for those who may not have understood, because I have really not told you the relation between a reaction and equation. But I will come to that in great details later on. But for the moment, for a particular phase, G is a function of pressure, temperature and composition. Any phase. For a pure phase, G is a function of pressure and temperature. Your chapter 1. Chapter 1, write up 1, the first one that I said to you. And for a solid solution phase, G is a function of pressure, temperature and composition. Now every phase has a particular G value. You know, say along this line, kyanite is equal to sillimanite, they are in equilibrium. Equilibrium means G sillimanite is equal to G kyanite. That means delta G, difference of kyanite and sillimanite, is equal to 0. If so, then you have an equation for a pure phase where it's a function of pressure and temperature. So these are the variables. These are the variables. Right? These are the variables. Now, every thermodynamic equation, therefore, thermodynamic reaction is an equation where there are variables inbuilt into it. How they are used, what they are, we will see. But those are all equations. Every thermodynamic equation, reaction, is a thermodynamic equation involving variables. For a pure phase, pressure, temperature are the only variables. For a solid solution phase, pressure, temperature and mole fractions are the variables. But we are at the moment dealing with Al2SiO5, which is a pure phase, and so this applies to us. So the unknown variables in this are pressure and temperature. And this tells us that if your composition, system component is Al2SiO5, 1, C is equal to 1, P is equal to 3, and then you have the variance is equal to 0. Meaning what? Meaning the number of variables is equal to the number of equations. Right? That means if you have now two variables here, isn't it? This is temperature and this is pressure. These are the two variables in this graph. Sorry that I did not write it earlier. So, if there are two variables, then there are two equations. You can ask, sir, but there are 3 lines, so there should be 3 equations. Yes, students, yes. There are 3 reactions. There are 3 reactions. But I tell you there are only 2 equations. I will tell you in a moment, metamorphic petrology is a few little related things that I have to tell you. Right. We will ignore that at the moment. The only thing that you should remember at this point, before I go into great details of that every thermodynamic reaction is essentially equation where you have pressure, temperature and compositions as the variables for solid solution phases and pressure and temperature for pure phases. Right? Correct. So now we have come to this where it is equal to 0. That means pressure and temperature, the 2 variables that are necessary for a pure phase, they are automatically generated. There is no unquantified variable. There is no unquantified variables. There are 2 variables and you have 2 equations. 2 equations. So you can solve it with the system, can solve it, and it tells you this is the pressure and this is the temperature. Right? Now, I will use a different pen. Let's say, I draw it with a different color now. Let's say the composition, I take a high pressure, eclogite facies, pellitic rock, which will have kyanite. And I can assure you that if you have analyzed that kyanite, you will get a substantial amount of chromium. Normally, you will have a lot of chromium. So now your composition is composition. That means I will write it clearly so you understand what you mean. So your sillimanite, kyanite, and andalusite, if you are looking at a high pressure thing, then it contains AlFe. Remember, this is trivalent. Kyanite, AlFe, again 3 plus, whole twice SiO5. And your andalusite is Al, Fe 3 plus, whole twice SiO5. So now, if I ask you for this Al2SiO5 phase diagram, what are the system components? What will be your answer? The answer will be Al2SiO5 and Fe2SiO5. Remembering that this is 3 plus. So you have two components now, Al2SiO5, Fe2SiO5. Now what happens? How many phases are there? 3. How many components are there? 1, 2. It's a 2-component system. Now if I ask you what happened here, equal to now for this 2 minus 3 plus 2 is equal to 1. There you go. There you go now. Now what it says, okay, if this is your system, then we have a problem at hand. What is the problem at hand? There is one unquantified variable. One unquantified variable. That means, in this case, variance is 1 for this composition of your alumini of your kyanite, sillimanite, and andalusite. Your variance now is 1. That means number of variables is equal to 1 plus number of equations. That means one additional data you need. One additional data you need. That means you don't have an unique PT value. It is not a variance 1. So this triple point is no more a singular point in a pressure temperature diagram. It is a function of something else. And what is that function? What could be the variable? What are the other variables now in this new diagram? You will soon see that now you have, because of this, you have added a complication to the system. It is no more this flat thing. Now you're where the point kyanite, sillimanite, and andalusite, where they coexist. Now it's no more an invariant point, but an univariant line. It is now an univariant line. So this point now is no more unique. It varies. But what does it vary on? But what does it vary on? Okay, let's look at these compositions. Pressure temperatures, of course, a variable. We have it on pressure temperature diagram. So what are the variables? You have a variable. What is the variable? Listen to me at this carefully. For this composition, I can write XAL is equal to AL divided by AL by Fe3 plus. And this is in sillimanite. Have you understood? So X Fe3 in sillimanite is equal to Fe3 plus divided by Al plus Fe3 plus. That means now you have XAl and XFE in sillimanite And you remember, this 2 should add up to 1. XAL in sillimanite plus XFE3 plus in sillimanite will add up to 1. So XAL plus XFE is equal to 1 in sillimanite. That means if you know one, you know the other. So if this is a variable, this is also, if this you know, this is automatically known. Same for kyanite, same for andalusite, you will know. These are not independently varying variable. One of them is independent variable, the other one is a dependent variable. Have you understood? So this, although you have written 2, but each of them is not a variable. One of them is independent variable. So if you know one, you know the other. So you have one variable from here, sillimanite, one variable from kyanite, and one variable from andalusite. One variable for sillimanite, one variable for kyanite, and one variable for andalusite. So in this system, how many variables do you have? Pressure, temperature, X aluminium sillimanite, X aluminium kyanite, X aluminium andalusite. There you go. You have 5 variables. Remember, this is 1 minus XFE sillimanite, this is 1 minus XFE kyanite, and this is 1 minus XFE andalusite. So you have 5 variables. Have you understood? It says that you have 5 variables, not 1. Not 1, not 2, not pressure and temperature. Yes, pressure and temperature if it was Al2SiO5. If it was Al2SiO5. The moment you change this, every mineral here, all the 3 minerals, can vary its composition between the 2 end members, Al2SiO5 and Fe2SiO5, and resulting, you will have these 5 variables. Pressure, temperature is common to both in black and red, but this variable comes in. Remember, if it was pure, then XAL sillimanite would have been equal to 1. XAL kyanite would have been equal to 1. XAL andalusite is equal to 1. That means it is self-constrained. But right now, you don't know. So you have 5 variables. 5 variables that are there, built in to this particular system, out of which the variance equation tells you, give me 1. Give me 1. And I will calculate. Rest is not important. Give me 1. And I will tell you what the other 4 are. So you need 1 input and the rest can be quantified. How? We will see. How? We will see. But going into the depth of it, this is very, very crucial. Phase rule, once again, you have a bivariant, a bicomponent system. And that has modified your earlier pure phase system into one variance assemblage. Sillimanite, kyanite, and andalusite in the presence of chromium. Sorry, where did I do? What did I say? Where did I say chromium? Okay, ferricyan. It doesn't matter. If it was chromium, it would have been something else. Okay, so in this bivariant, if this is the component system components, and these are the variables, then these are the number of variables. The Gibbs phase rule tells you that out of these 5 variables, give me an input of 1 variable. And I will tell you all the rest 4. How? I will tell you later. Have you understood? This is very important. So what has happened? this triple point now is no more an invariant system. It is now an univariant system. Why? You see, along at this point, pressure temperature is fixed. But if you are on this line, to fix the point, you need a variable. Say if you take this, then this will be the pressure. If you take this temperature, this will be the pressure. So the pressure and temperature values will change depending on these variables. And the Gibbs rule merely tells you, give me one. And the rest I can quantify. If you put in that I give you the value, then the variance drops to 0. If you can give the data, then the variance drops to 0 because you've given an equation. So have you understood? When you say input data, give me a pressure value. What you will say, phi p is equal to something. That's an equation. So you artificially increase the number of equations. So number of variables minus number of equations, the values. If you increase the equation, the values drops. So when you give an input value, the equation is hiked up, and so this difference becomes 0. So now you see, if you take this aluminium ferric ion system, then your triple point is not a triple point anymore. That is why I said, if your teacher asks you, what is the variance of sillimanite, coexisting sillimanite, kyanite and andesite, you have to ask him, what is the composition of your minerals? If your teacher had asked, what is the variance of coexisting sillimanite, kyanite and andesite in the Al2SiO5 system, he has told you the system. And then this blacking works. But if he has not, then I have many pens and I don't know which to use. You can ask me, what is the blue pen? We know what is your black pen. We know what is your red pen. What is this blue pen? There you go. Now what happens? This is my blue pen. Your sillimanite could contain chromium. And if you do that, then you can see C now is equal to 3. This now becomes equal to 2. And have you understood? 3 plus 3 plus 3 plus 2. So now your triple point, this point, kyanite, sillimanite, aluminium coexisting in equilibrium, it can move over space, not along a line, but on the space. So it has more variables. I will erase this and use the blue one so that you can see it. It's too crowded, this board now. So I will erase this. I will erase the black. So now I have just kept this. Yes? And I draw a line. Now, if you have this, what are the variables? Now you see, if I take sillimanite, then you would have XAl plus XFE3 plus X chromium equal to 1. Yes or no? Kyanite, X aluminium kyanite plus XFE3 plus kyanite plus XCr kyanite equal to 1. This is sillimanite. And then you have andalusite, X aluminium, andalusite plus X Fe3 plus kyanite plus XCr in this would be kyanite. This is also andesite, and this would be andesite equal to 1. Now you see, I have written this. I hope you have understood it. This will be it. I will just write one of them. So X chromium will be what? Chromium divided by chromium plus Fe3 plus Al3 plus. This will be. Similarly, for X Fe3 plus X chromium plus. So now, let's look at this equation. What do you see? You see something interesting. What is it? There are 3 variables. There are 3 variables in each of these equations. Have you understood? Out of that, if you know 2, the third is automatically fixed. If you take 2, if you know 2, or if you assign values to 2 of them, the third is known. It's not a variable. It's not an independent variable. It becomes a dependent variable. And this works for all the 3 phases. So now, we'll look here. What we should add here? How many variables should we add here now? Excel is all there. Now we add X chromium or XFE3 plus in sillimanite, or is important, or X chromium kyanite or XFE3 plus kyanite, X chromium andesite or XFE3 plus andesite. So now, gentlemen of the jury, you have pressure, temperature unknown. You have these 3 unknowns. If you were red, that means it was a binary system component. And now for a ternary system component, you have to have 1, 2, 3 variable. So you will have 2 plus 3 plus any of this 3. So you will have 8 variables. You will have 8 variables. If you have 8 variables, you should have 8 equations. Then you will get the variance as 0. But Gibbs phase rule tells you that f is equal to c minus p plus 2, c is equal to 3, p is equal to 3 and 2, and this is 2. Gibbs phase rule tells you, don't be stupid, don't waste your time. Yeah? Don't waste your time to find out what value actually. You do one thing. Nature is telling you, you do one thing. Be more intelligent than what you are. You give me 2. And the system will find the rest. How? We will see that. How? We will see that. But this is the very, very crucial thing that you need to know. It all started, all this complication started from 1 component system to 2 component system to 3 component system, black, red, blue. You increase the variable from pressure temperature when it was black to 2 plus 5 when you had 2 components. And then you bloody added 3 more because you made the sample complicated. It all started with the system components. It all started with the system components. That's why system components are crucial. That is why system components are crucial. And that is why Gibbs phase rule should be understood as a philosophy, not as an equation. Remember, Gibbs-Phase rule is only helping you out. Gibbs-Phase rule is telling you, out of all these variables that, remember, Gibbs-Phase rule tell you the numbers of variables that are needed. Gibbs-Phase rule tells you the number of variables that are unconstrained. Gibbs rule does not tell you what are the variables that can be constrained. No. Those are constrained internally by the system. How will they be constrained? They will be constrained via equations. What are these equations? These equations are reactions. We will talk about them later. But first let us digest this very crucial, central philosophy of metamorphic petrology. You can take any system and try it. Be just careful of what are you doing. And you will know. I will give you some problems to solve yourself. But this is very, very, very crucial to understand. Importance of system and phase components. We go back to the black pen. If you have any questions on this, I think you will not have. But you can write it on a mail, and or best is to write it on Google Classroom. It is best so that I can answer and everybody can see. That would be a very good thing. Try to generate a problem and put me in a wrong foot. It's difficult, but you can try. And one more thing about these classes that I am taking now. You will not get this in such great detail in books. You will never get it. Because then the book, it's not that the person who wrote the book does not know it. He knows it. Only thing, if he does this in so much detail, that book will be as big as Mount Everest. That is why he only gives you the tip of the iceberg. I'm trying to go deeper because I don't teach a lot. I want you to understand philosophies. I don't read chapters from a book. I will draw this diagram again. We have been talking so far about the triple point. Let us shift to any of these lines. When I draw the black pen means what? This is how it was. Blue, black, red. The same phases were there. Sillimanite, chirite, and andesite. Now, let us move in to this line. What is this line? It is where both kyanite and sillimanite coexist. Kyanite and sillimanite coexist. If I write it, an equation, I will start getting into it now. Al2SiO5 kyanite is equal to Al2SiO5 sillimanite. That's the reaction. So then, if you know this, then you should know at equilibrium, Gl2SiO5 in kyanite is equal to Gl2SiO5 in sillimanite. That means delta G of the reaction is equal to product minus reactant. Gl2SiO5 sillimanite minus Gl2SiO5 kyanite equal to 0. Gl2SiO5 in sillimanite is equal to Gl2SiO5 in kyanite minus sign, so delta Gr at equilibrium value should be equal to 0. And this delta Gr will be a function of pressure and temperature. Right? It will be a function of pressure and temperature. Now, back to Gibbs phase law. F is equal to C minus P plus 2. What is my C? I'm writing with the black pen. Al2SiO5. 1. How many phases? 2. Plus 2. Variance 1. Means what? How many variables do we have? How many variables do we have? Pressure and temperature. Because composition terms don't come in. Composition terms don't come in. So pressure and temperature. Right? Correct. So it means one of the variables, remember, del GRPT is equal to 0. That means G is a function of pressure and temperature, as I told you. That means if you know temperature, you will find out pressure, or pressure, if you don't know temperature. This guy is telling you, this phase diagram, guys, sitting on the table on the blackboard, it's telling you, boy, folks, you have one equation. It's telling you we have one equation. You have one reaction. What is that? Kyanite is equal to sillimanite. And you have one equation. Del Gr is a function of pressure and temperature. You have one equation and two variables. I can't find both for you. Go to hell. I can't find both for you. Go to hell. Give me one, I give you the next. I assign a temperature value and I get you the pressure value. Assign a temperature value, that means T is equal to something. T is equal to something. You give that equation, give me that value. T is equal to that value. Give me that value. And I will tell you what is the pressure, because I have an equation. But if you give me the T value, I give you the pressure value. Or if you give me the pressure value, I give you the T value. What? I can't give you both. The system cannot give you both because you have only left one equation. No more. Right? But, if you use the red pen, right? How many equations will you have? You will say, sir, I have 3. Now let me tell you, what are the equations you will have? Let me give you an example. You will have kyanite is equal to sillimanite. Yes or no? You will have sillimanite is equal to andalusite. Yes or no? And you will have kyanite is equal to andalusite. Yes or no? Why? Now you see a trick here. Although you see 3 reactions, they are all not true. I will tell you what true means. You see, if I take this 2 and eliminate S, I get back this. Have you understood? If I take this 2, eliminate S, I will get this. So this equation here is a derivative. It is not an independent reaction. It is, it's an algebraic addition to 2 equations. If you look at it this way, I take these 2 equations and eliminate the common phase, I get this. So you see, although you see 3 reactions, out of which 2 reactions are independent, 1 reaction is an algebraic addition of the other 2 independent reactions. Other 2 independent reactions. This is a very, very important point. I will elaborate it in my next lecture. But the important point that I want to make, although you see 3 reactions, all 3 reactions are not independent reactions. 2 of them are independent, 1 is dependent. So in effect, if you're using all 3, you're going back like a dog biting its own tail. You go round and round in the logic. So here, it doesn't work. You have 2 independent reactions. Choose any 2. You don't have more than 2. So, what does this Gibbs phase rule now tell you? For if you have this phase diagram, it tells you this will be 2. Isn't it? Because this will be 2 minus 2 plus 2 equal to 2. So this will not be univariant, but it will be bivariant. Have you understood? Bivariant. That means this will be bivariant field. That means its position, which was unique for this black pen, now moves over space because of additional variables. What are the variables? XAL kyanite, XAL sillimanite, XAL andalusite. It is variable. So the position of this reaction is not unique as in the black one. It's not unique. The position is changing. So now you see here, if I draw the same line here, you can see, I draw the same line. The temperature is still there, but if the pressure was, it would be here, or here, or here, or here, depending on what is the composition of kyanite and sillimanite. Because now your variables are there. What are the variables? Pressure, temperature, XAL sillimanite, XAL kyanite, XAL andalusite. So based on the variables, any 2. So if you say, okay, this is my temperature and this is my composition, then immediately this is the pressure that you find out. But if you had the same temperature but another composition, you would have another pressure. That is why Gibbs rule tells you, give me some, I give you more. Give me some, I give you more. That is the very essence of the problem here. The Gibbs phase rule is a very, very logical, very powerful tool that immediately tells a metamorphic petrologist, as a professional, where you're standing. What you want to do, what you don't want to do, you be careful at this stage. Right at this stage, wait and think. So this is very, very crucial. So when the Al2SiO5 was pure, this kyanite sillimanite had a line, unique line. But when this became a bicomponent system, then the equation that you were using here doesn't work anymore, and this is the equation that varies. Pressure, temperature, composition. What are the X's? X aluminium in kyanite, X aluminium in andalusite, X aluminium in sillimanite, just like I told you before. So now it becomes a more complicated function. So now it tells you that, okay, whatever you do, I want two variables. And I explain this line now starts to move, which had a unique loci, which had a very unique loci in a PT diagram, now moves here. So, although you assign a temperature, that means you reduce the variance, you still have one more variance to contend. And this now is line. So you have to assign now not only the temperature, but also the composition of a phase, at least one. And then your pressure becomes fixed. Say, if you take a pressure, then you can see, if you take this line, then this line varies. You can assign a pressure value, you decrease the variance by 1, but you still have difference in pressure temperature depending upon the position of the isoplate. So you need to give a composition to get the exact pressure. And that is what Gibbs phase rule is telling you, cautioning you, is urging you to give the data. How you will give the data, what you will give the data, that's a different thing. That we will do later on. But that is what the Gibbs phase rule says. So this kyanite sillimanite is moving in a binary field. In a binary field. Do you know, in a pressure temperature field, its loci is nomofixed. Its loci is moving as a function of the composition. And so if you want to get a pressure value or a temperature value, you have to give two additional variables so that you get it. And that's about it. So this is what happens. This is what is very crucial for you to understand. Now, you can imagine. Will it? Okay. Now, what happened? Oh. Blue pen. Even this is not enough. Even this is not enough. Now your kyanite sillimanite becomes a multivariable system. Now you see, you will have 3 minus 2 plus 2, and this will be 3. Did you see that? So now then, you can't use even a binary diagram to show you. You have gone into a multi-component system. Even the simple minerals, you have gone into multi-component systems, where actually the reaction curve is more now a surface on a multi-dimensional space. Not a binary space, not a ternary space. It's a multi-dimensional space. And you need more variables to constrain the position of the kyanite is equal to sillimanite line. You need a lot of a 3-dimensional space to draw the surface of the plane. The last one was a line when it was pure phase, then it went into a surface, and now it's still a surface, but in a 4-dimensional system. It's a 3-dimensional system. Now previously you still could work with a 2-dimensional system when you had red, but now with the blue, you're off. You're gone into what is called abstractism. That's where metamorphic petrology is so complicated. But it's very logical. It's absolutely logical. There is no uncertainty. There is nothing to mug up. It's just that you have to understand it. And things are done. You don't have to read a lot. Of course you read a lot, but what I'm trying to say is you don't have to memorize in metamorphic petrology. Absolutely nothing. Just like in structural geology, don't memorize. Don't memorize. It's no use. Stress strain diagrams, whatever you take in structural geology, pure shear, simple shear, you can take fracturing. You know, what is there to memorize in structural geology? Nothing. There's nothing to memorize in mineralogy and crystallography. Nothing. Absolutely nothing. If you had to memorize, there is something wrong with the system. Metamorphic petrology, you don't memorize. The moment you have to memorize, you're gone. Don't try to get it from memory. Just take it as it comes. Okay? I think we will stop here. I hope I've been able to impress upon you the importance of system components and phase components. Metamorphic variables, how they work. Next, we will come to a very, very important, interesting thing. And that I will do in the 5th lecture. Thank you.